First and foremost, we'd like to thank everyone for attending today's webinar. We greatly appreciate you guys take time out of your day to listen to us present. My name is Mitchell Robinson. I'm the marketing coordinator here at ThermTest. And in today's webinar, Dale Hume, president of ThermTest, will be presenting on comparing three methods of anisotropic graphic composites. Dale will be speaking here shortly, and he'll be taking that over. But firstly, I'd like to mention as well of our next upcoming webinar happening on April 20th at 10 o'clock a.m. Atlantic Standard Time, and it will be on phase-changing materials for energy storage, presented by Dr. Sophia Malona. At this time, I'd like to say that if anyone has any questions, comments, and/or concerns, please type them into the question box, and we will address them at the end of the presentation. At this time, I'd like to pass the buck off to Dale, and he'll present.
Thank you for joining on this, what I hope will be an informative presentation. So we'll talk a little bit about three thermal conductivity methods across graphite and some other anisotropic samples that we've added to the presentation to round it out a little bit better. So let's proceed. So a little bit on the agenda. We'll chat a little bit about thermal resistance and thermal conductivity, what those are, what is effective or apparent thermal conductivity when testing anisotropic samples. These two particular slides I usually talk about with every presentation because they do have an influence on the way we discuss and present results. Who cares about thermal conductivity? Thermal conductivity methods for anisotropic materials. So we're more or less in this presentation focusing on methods that are typically used for measuring thermal conductivity materials. And then we'll present some experiments on some anisotropic materials using these three methods and have some discussion on those results. So what is thermal resistance and thermal conductivity? Thermal resistance is the ratio of temperature difference across two faces of a material to the rate of heat flow per unit area. The higher the resistance, the lower the heat transfer. The lower the resistance, the higher the heat transfer. This is the most appropriate method of characterizing non-homogeneous material when other modes of heat transfer through a material are present, in addition to the conduction. Thermal conductivity refers to an intrinsic ability of a material to transfer or conduct heat. It is one of the three modes of heat transfer, the other two being convection and radiation. The higher the thermal conductivity, the higher the heat transfer, and the lower the thermal conductivity, the lower the heat transfer. This is the most appropriate for characterizing homogeneous materials where the only mode of heat transfer through the material is conduction. It's an intrinsic physical property of the material, so that sample has a value independent of thickness or dimensions. And we'll talk a little bit about those two last items. So effective or apparent thermal conductivity. You'll see this description used quite often when there's some complexity in the measurement or the method itself determines it should be described that way. What we tried to do is create a little bit more awareness of what that means and what the reporter should be describing when they say effective or apparent. So in its meaning, the thermal conductivity has been measured as close to possible to the true value. There are identified sources of error which affect the measured accuracy. So what we'd like to see when those results are displayed or reported internally or externally, what are those examples of error, if they're known? In the measurement of anisotropic materials, those some sources of error are perhaps a poor fitting to a calculation model or the effects of heterogeneity on measurements. Those are both, as well as possible convection radiation effects, but we're really focusing on, in this particular webinar, is on solids. If you do have an interest on these same discussion points on rigid insulation materials, this is a link to a webinar that has similar conversation of what we're going to talk about later, but specific to insulation materials. So instead of the guarded heat flow meter in comparison, we're actually comparing the heat flow meter. And that's a really interesting presentation if you're measuring insulation materials. It explains quite a bit of bias that you can see in publications. So who cares about thermal conductivity? Academia, of course, and general characterization. R&D, basically to develop materials to increase or decrease the rate of heat transfer. Quality control, so that might be continuous measurements on the same sample where you're looking for a pass-fail situation. Specifications, this would be reporting of results on a material. And another really important one is thermal simulations. I pull out a slide specific to this. Typical simulations are done steady state, one-dimensional, with constant thermal loads on a model to determine temperatures, heat flows, and heat fluxes. Of course, additional transient analysis can be performed to determine initial conditions. Measurement errors from your materials are transferred through to the simulations. So some of the things we're going to talk about in future slides are an effect of this. If your results, now what's really important is all of the data that we generate in this webinar and across the various methods are watts per meter Kelvin. So if you back up a little bit, consider the method and the materials, these are some of the errors that can affect your simulation and the accuracy of your simulation. If your data is truly not one-dimensional and you're presenting it as one-dimensional, so if it's an average result for an anisotropic sample, that's an important consideration. If you're not measuring, rather your data is not representative of steady state. So if you measure a heterogeneous material, a macro heterogeneous material with transients as an example, you can have data that would not be equal to the true value of that particular material in its dimension. So transients are really designed for homogeneous material that fit the calculation model, and materials that are non-homogeneous are typically measured with a thermal resistance or steady state. And of course, other modes of heat transfer, such as convection radiating, thermal shunting, again, that's an effect of having an overestimation of thermal conductivity due to thermal shunting across fibers or particles within a matrix. And we talk about that in other webinars, which you can see on the webinar section of our website. So the three methods we're going to discuss that are commonly used for anisotropy measurements are the transient plane source or a modification of it. Time scales or measurement times are typically 1 to 80 seconds. That would depend on the dimensions and the thermophysical properties of that sample. Typically, you want to keep your heat within the dimensions of the sample, so those physical properties and dimensions determine the test time that you can use. A transient of temperature rise versus time is recorded, where slope is determined to represent thermal conductivity and thermal diffusivity. Small sample sizes, typically on the 10 to 75 millimeter scale. Of course, there's lower than that, larger than that, depending on the situation, but those are typical. You do measure with this method thermal conductivity and thermal diffusivity. There's various calculation models within this method. One of them being isotropic. That again, we talk about that in another webinar. In this webinar, we're going to talk about the anisotropic calculation model. Regardless, both of those calculation models are based off of a particular assumption of the material in the isotropic one, that the material is in fact isotropic and homogeneous, and in the anisotropic, that your material is highly organized in its directional properties. So through the thickness, if you have anisotropy, that through the thickness, it's repeating and well-defined and repeating. It also, the calculation models also are based off of 100% of the heat introduced from the sensor into the material is through the mode of conduction. Any other mode of heat transfer will incur error. The user can see that error in the residual. If they ignore that residual or accept that there could be some small error or even larger error, as long as they're aware of that and report it as apparent or effective with some definition, that might be okay. But it is an important consideration that you know what you're testing, know how the fitting is against the residual for that calculation model. The second method would be laser flash. Again, these slides are just giving a little bit of an introduction to the method used. We're certainly not trying to describe all the theory of each of these models. We're really focusing on the use of them in the application. There's a short energy pulse applied to one side of the sample and a temperature rise of the rear face recorded with an infrared detector. The recommended sample size is 1/2 inch diameter and thickness is up to a few millimeters. The recommended thickness would be really defined by the thermal diffusivity of your material. Again, designed for homogeneous materials. If you do want to measure anisotropy with this method, you do get a through thickness value with your standard measurement. For in-plane, there's two approaches. You can cut a sample in the direction of heat flow you want to measure, or you can use a in-plane holder plate and mask that will do the in-plane as well. We focused on cutting pieces according to the desired direction in our comparison today. We think that's the simplest way to describe these measurements. And lastly, the guarded heat flow meter, which is a steady state method. Unlike the heat flow meter, which again is from another webinar, which is meant for insulated materials and uses large sample size to get a good average of heterogeneous materials, as most insulators are. This method is for medium up to medium thermal conductivity, so up to approximately 40 watts per meter Kelvin. The sample size, typical sample size is 2 inch diameter, that's fixed. The thickness can vary up to 1 inch thick. So you can do different thicknesses based off of that standard 2 inch diameter. It does measure thermal resistance, and from the known conductivity, the system calculates, or method calculates thermal conductivity. Again, it is designed for homogeneous, of course, as well as heterogeneous materials. So anything that is between those two plates that come together, you will measure as resistance. It is guarded, so there's actually an oven that surrounds the sample that is set to the mean temperature of the two plates so that your lateral heat loss is minimized, so that you're measuring a one-dimensional value through a material. It is a very attractive method for measuring complex layer structures, which is one of the phenomena we'll see in some of the application of this method. So through the measurement of resistance, you can see effects of conduction, convection, and radiation. Are those phenomena desirable? No, but at least in the description of resistance, it's more appropriately measured. Contact, one of the comments not missing out of this is actually there is a paste applied to this method. So through the procedure of calibration, the effects of that contact paste are removed against known materials. So let's discuss one of the materials we sourced, as by the name of the presentation, was graphite. And we sourced what we thought, based off of the supplier, was going to be an anisotropic graphite. Well, we prepared samples, started making measurements, and we realized that it was in fact not very anisotropic. So what did that do? Well, you can see from the laser flash, which we prepared samples of 10 millimeter square. We prepared samples for each direction, one through the thickness or through plane, and the other in plane. That method measured very well because of the small sample size that it requires, and we have good values, valid values of diffusivity and conductivity for the two directions. But the anisotropic measurements for the TPS were not possible because the thickness of 1/2 inch and the shortest test time that we have available for this method is 1 second. We would overpenetrate the thickness by double, actually. So therefore, it put this particular material out of range for the TPS, and of course the GHFM, it put it out of range as well, limited to 40 watts per Kelvin. So we were really relying on the difference, the high percentage of anisotropy, to have a through thickness value that would be in the range of measurable. That wasn't the case. So what we did, we looked at this data and said, well, maybe we can create a situation of reducing conductivity through a laminate structure and give us the ability to measure and do some comparisons. So we introduced to the same samples, that's actually the graphite sample, we introduced a Pyrex disc and measured this stack or this laminate structure with the transient plane source, and the guarded heat flow meter. We have a volumetric, one of the inputs for the anisotropic measurement with the TPS method is the volumetric specific heat. So that volumetric specific heat is calculated for use in the calculations for that method. So we went ahead and made these measurements. If you're curious, the Pyrex side was facing the TPS sensor. So we did, as typical with transient methods in general, when you want to explore a fitting, you can do that through varying your test time. So in this case, we did different laminate structure, or through the laminate, we did different time scales, 4, 5, 10, 20 seconds. As you can see, the bulk conductivity and the other properties on the 4 seconds are all quite similar, as the heat is staying within mostly within the Pyrex itself. And then as you penetrate past the Pyrex, that structure is no longer repeating and well organized. So it's really not unexpected that these results would not be truly representative of the sample through the whole thickness. But it's an interesting phenomenon to see. So basically, you see some sensitivity due to the heterogeneity nature of that. Again, if you were to use any one of these timescale results, whether it be average or anisotropic, the fact that it changes throughout its thickness, the rule of thumb would be to measure as much of that thickness as possible. Great care would have to be taken, because the steady state comparison, or the measurement of resistance comparison based off thickness, should be similar. As you can see, it is not. But in this case, it's the major problems with the calculation. The anisotropic calculation model has a very poor fitting, and then errors is part of that. The GHFM results, again, based off the full thickness, which would be the Pyrex plus the graphite, results in a through thickness thermal conductivity of 5 watts per meter Kelvin. So we wanted to find an anisotropic material that we could measure that did represent well organized and within the range of these 3 methods, and that's the material we did next. Actually, there's one slide on the observations before we proceed. So the observations on this testing is in the materials we could actually test being graphite and the Pyrex laminate. The long scale times, which are typically rule of thumb for measuring materials like this, were not truly representative of the material, and that's due to the non-repeating anisotropy causing errors. The LFA data, we were able to get good results on the graphite by itself because of the sample size that method requires. There is some level of anisotropy in that piece, but not the degree that we were hoping for. That would put the through thickness value in the range of these other 2 methods. And the GHFM, again, graphite by itself being 130 watts per meter Kelvin plus, put it at a range, but the Pyrex plus graphite laminate gave us a resistance value and thickness equal to around 5 watts per meter Kelvin, which did put it in the range. So there's good correlation, rather poor correlation between methods when comparing samples with layers that are non-repeating. So what's the other phenomenon? What does it look like when you do have a material that has good repeating anisotropy through the thickness? So we found an anisotropic carbon fiber and prepared the samples much in the same way. 2-inch diameter by 1/2 inch, 2 pieces for the TPS method. Laser flash, we took 10 by 10 squares, 10 millimeter by 10 millimeter squares from each direction. And then we took one of those 2-inch by 1/2 inch samples for the GHFM. And as you can see, the different time scales give us the same result on the TPS. That's because if you look at the fitting and the time scale and penetration for each one of those times, the internal structure is well organized and repeating. So that means if you compared this to glass, if you measured glass at different time scales, whether it be with the isotropic or anisotropic, you would get the same number at different time scales. So it's really important to understand that concept, that if you have layers or non-repeating anisotropy, the true value of that sample is based off the entire thickness. That's the only way to truly consider it. Otherwise, you have some number that is representative of some portion of the material's thickness, but not the full thickness. And as you can see, we have good correlation with the laser flash and the only measuring capability of the Garda heat flow meter being through the thickness. So there's actually quite a good correlation between these three methods and the different time scales, really proving that through the thickness is repeating, and this is a good candidate material for measuring by any of these three methods, and that's why you have good correlation. I often get, will I get good correlation if I compare data to another method? If you look at the calculation model and the method that is you're considering, if your material falls within the design purpose of that method, you often will get good correlation. It's when you use it outside its design range that you get poor correlation. So to close the loop on this, we added Pyrex and stainless steel slides because we were curious to these same carbon fibers and wanted to just compare the data and see how the thermal conductivity changed, thermal resistance and thermal conductivity. So we took the same half-inch thickness carbon fiber and included a 2 millimeter thickness as Pyrex and then a 3 millimeter thickness of stainless steel and made those same measurements again. And as you can see, due to the thickness of the carbon fiber, when you consider carbon fiber and 2 millimeters of glass, the carbon fiber is by far the dominating resistance. There's very little change if you compare that thermal conductivity to the other from the previous measurement. And then stainless steel, of course, that did change the thermal resistance and thermal conductivity to some extent, but of course you're getting a dominating and insulative effect. If we can call carbon fiber through thickness insulating, you're getting the effect of that. We did not do this with other methods due to basically these not being good candidate or suitable materials for laser flash because of the dimensions involved and the non-repeating nature. We would have ended up with data that was very similar in terms of the error associated with each. So some observations on the measurement of carbon fiber is the carbon fiber results were representative and accurate, and that's because that material is truly repeating and well organized through the thickness. Again, you should be able to measure that if you're considering a transient method, and you should be able to measure at different time scales or different depths of penetration, and those results be similar. Again, the rule of thumb is to, when you're measuring heterogeneous material, to measure as much of that as possible with a transient method. If that's the case and that's the method you have, just be aware of how to describe that effective nature. The carbon fiber plus Pyrex laminate, long time scales would not have been representative. I didn't display that data here, but you would have seen it as non-representative and non-repeating anisotropy errors in the anisotropic calculation model. LFA, we weren't able to do the graphite plus Pyrex, but the carbon fiber by itself showed good correlation with the TPS anisotropy and the Garda heat flow meter. Again, that method is well suited for extracting pieces in the direction you want to measure. So the takeaway is if the samples are highly organized and repeating through the thickness, you can have good correlation. And then the opposite is true when you have disorganized anisotropy. In this case, we have a laminate structure or layers, if you will. This same phenomenon exists with particles. Introduce particles within a matrix, and in other webinars we talk about this, and you can introduce new phenomena such as thermal shunting. We talk about that in other webinars. So final thoughts, thermal conductivity is not simple. There's no one size fits all. There are certainly ways to stretch methods and be aware of that, how you represent the data. That's the way we've kind of feel about. We have a variety of methods in our lab, and we try to look at them and share data based off of the primary function. In the TPS, typically with transient methods, your material should be micro-homogeneous, and the anisotropic, based off the anisotropic calculation model, highly organized and repeating. Again, heterogeneous materials can be in fact measured, the rule of thumb being to measure as much of that sample as possible, but fully consider, am I measuring the entire thickness? And there's some complexity in that. The other thing to keep in mind when using the TPS for considering your full thickness is the reported penetrations with these methods are based off the accuracy of the diffusivity that is reported within the method. And that accuracy of the diffusivity is based off of satisfying some measurement parameters. So you can have error in your diffusivity, which will give you some potentially misleading penetration depths. So there really are really some really critical phenomena to keep in mind when measuring anisotropic materials that are non-repeating. The GHFM, our guarded heat flow meter, designed for measuring homogeneous and heterogeneous complex structures, can be measured as you introduce them between your plates. The data is guarded. Again, this is for more mid-range conductivity, so there is a guard introduced to encourage one-dimensional heat flow. Micro to macro heterogeneous materials are possible. The true thermal conductivity based off of the full thickness of resistance is what we encourage. When we encourage this method, that is the desired outcome. Excuse me. Glossary of terms, this is mostly introduced so that people can look at it while they're watching or recording. I will point out a few additions compared to other webinars. The guarded heat flow meter, but the particle shunting as well. I've mentioned that within this webinar. If you want to read that or look at the other webinar or have any questions, please feel free. And that is the end of the presentation. So if you have any questions, I'll read the questions out loud and try to answer them the best I can. So here's a question. What is the exact meaning of mean temperature? Some questions ask us to report the thermal conductivity when testing at 10 degrees. Some ask us to report at 35 degrees mean temperature. It's a very strange request. Well, if you are using a steady state method like a heat flow meter or guarded heat flow meter, the mean temperature is the average between the two plates. With the heat flow meter, your delta T across your two plates could be 20 degrees, 15 degrees. With guarded heat flow meter, it's typically 25 or 30 degrees. The mean temperature would be the average between those two plates. So if you want to measure at different mean temperatures, you would tell the system to heat the two plates to that mean with your delta on each side of it. In transient method and laser flash, both of those methods have an oven that the samples would be heated to that temperature. The conditions would have to be isothermal. Typically, those methods have some automation in determining that. Once temperatures are isothermal, measurements are done. So in that case, mean temperatures are referring to the environment temperature. The transient methods work off of a small temperature rise above ambient conditions, typically 1, 2, or 3 degrees, where steady state uses a mean between the two plates. Hopefully that answers your question. What is the better method to measure anisotropic polymers that have added conducting fillers on my experience? That's a complex question. There is another webinar, more than one, that I would refer you to if you were to go to our webinar sections, skip through some of the more boring audio and get to the slides that are specific to your question. There's some graphical representation there as well as real data. With fillers, fibers, with fibers, if they're well aligned, well aligned and repeating through the thickness. A good example is the heat flow meter webinar I did, which was using NIST 1450D, which is a certified material for calibrating the heat flow meter. Those fibers look well aligned under a microscope, but they're in fact they're well aligned but non-repeating, and we were able to show that through the comparison of transient anisotropy measurements as well as steady state. And then we show the estimation of the anisotropy with steady state by cutting that sample in slivers and turning those pieces 90 degrees, and you can see that there in fact is anisotropy, and it doesn't correspond to the transient. And with transient, different time scales and sensor sizes, again, because those are the typical rule of thumb to measure as much of that sample as you can see that time scale and sensor size in that case is not giving you a large enough representation, or has other errors because of the non-fit or poor fitting to the model, calculation model. you get poor results. And you really never do get results that correlate really well. There's one time that correlates well. It just so happens by coincidence that it's 3/4 of the way through the thickness. Again, this is on the heat flow meter webinar on a similar topic. So it can be a little bit complex, but if your materials are well aligned and repeating, really the transient method would be fine. If they're not well and repeating, a steady state method would be ideal because you're measuring resistance of the whole sample. Therefore, your one number is truly based off the full sample thickness. To calculate the thermal conductivity of TPS measurements, the density and CP are required. Yes, that is correct. How do you determine the CP for the examples you showed here? So for the specific heat on the non-laminate, so the straight anisotropic materials, we measured those. That's a good question. I hinted at it, but we measured those with a DSC. So we measured the graphite and the carbon fiber. So again, not layers. We measured those with DSC and measured the density by scale. And then with the laminate structures, we did a volume percentage rule of mixtures. Hopefully that answers your question. How to measure thermal conductivity of fabric or cloth? Yeah, that's a really difficult material. That echoes the question about if you have anisotropic in your fibers, how do you measure it? There are those that say they can measure fabrics with a high degree of accuracy for through thickness value. That's somewhat complex. If you're using a transient method, of course, a fabric will have other modes of heat transfer due to convection. So fundamentally, if you're looking for the true value, use a resistance-based measurement. If you need something quick or an estimation of those properties, and you've fully considered your dimensions and how the different time scales affect your results, you could consider a transient method, but with great care. And you would report that as effective or apparent with a description of why it is effective or apparent. That's really important. So many people just would describe results as effective or apparent without a description, and it leaves the user, rather the reader, confused or assuming that there's as true as possible without a description of what makes it less true. How do you account for differences in radiant energy absorption with LFA based on material type? In other words, how is transmitted radiation accounted for? In these cases, for the LFA data, and I'm sorry, we didn't go into a great deal on all the sample preparation for each of these, but for the laser flash samples, these were prepared as the ASTM describes, as well as the manual for our laser flash model. A graphite coating was applied to both sides of the sample. We typically will clean the edge of the disc, if you will. In this case, it was a square, not a disc. We clean the edge so that we keep the heat penetration on the coated side, and that helps disperse the pulse across the surface of that sample, and the method detects the infrared on the other side. Hopefully that helps. We didn't apply any major corrections because these samples were well within the range, and the results, I think, support that, especially the good correlation between methods. What is the best method for measuring sandy materials? Well, nor does the method describe to. Certainly laser flash is one you would not use due to porosity. And how do you, that method requiring parallel surfaces that are uniform in thickness, that's a difficult task. Transient plane source can measure. Great care should be considered when you look at the size of the diameter of sensor and time scale you're doing. Sand on a guarded heat flow meter is tricky. You're going to have error associated with the contact. It's very difficult to apply paste to that. You could use that as a qualitative or an estimation of the thermal resistance. So it's a difficult task. Of course, there are other methods that are not discussed here, such as transient line source. That has the same considerations as the TPS method, that you want to make sure you're using a sensor with enough volume penetration and that you're removing the nonlinear portion of the data, which still is going to have some effects of other modes of heat transfer in it. But given how typically the data is used in sand, it's typically averaged out with testing many samples, and if this is for a geothermal application, different depths. So statistically, you hopefully get a good average based off that approach. So hopefully that's helpful. With transient methods, if it's if it doesn't have if it's not wet, if it's just dry bulk sand, you probably want to keep your temperature rise low so you minimize effects of convection. Is the GHFM useful for very heterogeneous materials like a brake pad? Absolutely. Anything, what's really critical about transient steady state methods in this case, brake pads, at least some brake pads have particles in them. If you're using a transient method and those particles are in the path of heat from a transient sensor, you're going to get shunting. The amount of shunting is based off the dimensions of your particles, the difference between your particle dimension, the difference between the thermal conductivity of your particles and your matrix. You can have overestimation of transient data, where if you measure steady state, there is a transient effect of that. Of course, when you introduce a sample between two plates of a different temperature, there's going to be a transient effect due to that shunting, but data is not finally recorded. Resistance is not finally recorded till steady state condition is met. So that means all those phenomena of shunting and if there's any other phenomena, those are mature. You're measuring just the resistance. So if you do have a brake pad that is well organized and repeating, it's okay. If you're using a bulk or isotropic, your data will be more favorable if your particles are really small and random. If they are large or high difference in thermal conductivity from the matrix, you can have error. You will see error. You might not see if you don't have another method to compare it to. Again, one of the ways to investigate that is different time scales to see if your data is changing. But again, time scales can also be just proportionally affected. So if you're having shunting, you can have just the same proportion of that phenomenon happening at different time scales. So again, consider the method in its ideal application. And when you report the data, describe some of that as effective so that there can be some consideration. Again, if you were to use data that has some overestimation in a simulation, when you run your typical 1D steady state simulation, you can have error. Which is the easy method of these three to measure conductivity? It's a difficult question. I usually, when it comes to easy, it can be a loaded question. I like to start with what's the most accurate method, what's the most appropriate or suitable. So if the question is first, what's the most appropriate, I would basically have a conversation around what we've talked about here, and then looked at where's the setting of those measurements and try to find which is the easiest. There are some really wonderfully commercially developed methods, like our laser flash is a rather new one, and I have an old one, and the commercial development of that laser flash has made it much easier to use than the early model. So there are certainly commercial considerations that can be done to a method to make it easier to use. Is it possible to measure the thermal conductivity of these two materials, polymer backing and fabric, using the MP2? With the MP2 with the current sensors available, no, unless you're interested in measuring a qualitative feel for warmth or cool. I'm not describing that as a quantitative measurement, nor the associated quantity with it, because of, there's a lot of discussion around this quantity, and that being thermal effusivity. Care should be taken to, whenever I describe that particular measurement approach, there's a caveat. It should be considered for just relative comparison between two materials, how they feel to the touch. Thermal conductivity should not be backed out of that property in that situation, because again, you're measuring a transient with a transient on a material that has other modes of heat transfer, you're going to have error in that. And if you pull out the thermal conductivity and feel like, rather determine that to be, or by definition describe that as accurate, that would not be truly accurate. It really should be described just as qualitative feel for difference. So right now with MP2, we do not have a sensor that qualifies for these measurements for thermal conductivity, at least not with MP2. Thank you for the presentation. I have a thin coating on copper. The coating rather is made of copper particles, graphene nanoplatelets. The thickness of the coating is around 5 micrometers. How can I measure this? Well, that's a difficult task, but there are certainly methods to describe that, rather to test that. You'd be probably looking at a thermoreflective method, and the reason is you have a backing of copper, which is roughly 400 watts per Kelvin, so it's a big heat sink. So if you're looking to measure the intrinsic properties of the coating, again, you have same considerations. You want to measure as much of that that coating as possible using, as with other methods, the thermoreflectance methods have the ability to change timescales to have different amounts of the material included in the data. Care should be done with that, and different timescales considered so that you know you're measuring an accurate value. One thermoreflectance method you may consider is the steady state thermoreflectance method. There's some information on our website, or if you want more information, just drop your email to Mitchell and we'll send you information on that. But nothing in what we've talked about here really would be ideal for that. 5 micrometers on top of copper would be a difficult task, especially if you're looking for the intrinsic properties of that coating. I wish to participate in more webinars. Okay, you're welcome. Of course. Does the data obtained from MP2 accurate enough to use for publication in peer-reviewed journals? There's a number of sensors. If you're using, and we describe those sensors in their primary function. So we want you to use them according to the way they were designed to be used. So there is an example of that. There's a transient line source needle available with the MP2. We do not want you to use that method, despite other makers of transient line source testing liquids. We do not want you to use that for liquids. There is a transient hot wire sensor, which is a primary method for measurement of fluids. That one is much more appropriate. If you look at the accuracy and repeatability statements, if you're measuring within that range that we state, you should be fine. In fact, it's far superior than using the transient line source for fluids. The reason why is quite simple. A typical measurement time on transient line source is tens of seconds. It's very difficult to make a measurement of fluid with a transient method, tens of seconds, generating several degrees of temperature rise in non-convective effects of convection. A colleague of mine did a webinar, I think it's in the series, that compared 3 methods across fluids. So as an example, if you want to check that out, again, so if you look at the primary function of the different sensors that are available, certainly peer-reviewed journals could be possible, again, as long as they're used appropriately. I think I got everybody. So if there's no more questions, I appreciate the time. Is there an example of such publications? Certainly. If you look at transient hot wire, there's many hundreds of publications. If you look at transient line source and the measurement of soil, there's many publications. We're happy to share those. We could do that. So if you want to drop my colleague Mitchell an email, we'll be happy to share those with you. Which have used MP2. So again, MP2 is a relatively new system. It's the sensors, the theory behind the design theory behind the MP2 is that we've taken some of the sensors available in our lab scale equipment, such as the THW L2 and L1, which does have many publications, and designed a smaller operational range that can be plugged into a platform-based controller that you can have multiple sensors. So if you look at the lineage of those sensors, where they come from being our laboratory systems, there are many publications, but specifically on the MP2 with THW sensor, for example, you may not see that exact model, but you certainly see ThermTest transient hot wire, which is one of the sensors. Similar theory, determined by an ideal measurement approach. Certainly there are plenty of publications. Any other questions? Thank you. You have a good day as well.
Perfect. Thank you. for participating in today's webinar. If you couldn't make it, or if you joined early or late, the recording for this webinar will be released on Friday through email and can also be found on our website at thermtest.com. Thanks again and have a great day.